Okay, so I'm going to share yet another Z80 experiment I did a couple days ago. In this case, I'm using the Z80 to generate an 8-bit sine wave. So what you're looking at right here is an oscilloscope display of a digital sine wave being generated by my Z80 computer. So I'm going to go into some detail about how I did this and how it works. So anyways, if you look at the sine wave itself, each individual wavelength is split up into 20 segments. And so from, for one individual period of the sine wave, I'm splitting it up into 20 pieces and defining discrete voltage values. And those voltages, well, actually those values are encoded as 8-bit numbers. So what I'm doing is I'm reading data from the data bus, and I'm feeding that into an 8-bit digital to analog converter. So for example, if I want to put out 0 volts on the digital analog converter, I put 0 on the data bus and send it to the digital analog converter. If I want to put 5 volts out there, I put the hex value FF, because it's the largest 8-bit number. And so it does 256 different voltage values from 0 to 5 volts. So that's how I'm generating this sine wave. It uses an assembly program that cycles through, for each individual wavelength, these 20 different voltage values. I'm sorry, these 20 time steps. Anyways, if you've seen these videos before, you've probably seen my breadboard a million times. For those who have not watched before, I'll do a quick review. I have my Z80 CPU running here. That's the chip right here. I have some address decoding. Actually, this is like instruction decoding right here. I have the address bus, which is those 16 flashing red LEDs, and the data bus in green, which is flashing so quick that you can't really see what's going on. It just looks like they're on constantly. And down here, I have an EEPROM, which has my program that's being used to write the sine wave to the data bus. And I've got another set of LEDs over here, which is also that encoded binary data that's used for making the sine wave. So you can actually, if you watch closely, you can notice the LEDs oscillating back and forth. That's as the binary values span the range from 0 to 255 to make the sine wave go from 0 to 5 volts. So you can see when all the LEDs turn off, it's at the minimum value, and when they all start flashing, you're approaching the maximum value. And so, anyways, right here, with these 2 flashing LEDs, you see the chips behind it. The one on the left is the digital to analog converter. The one on the right is actually an 8-bit NAND gate, which I use for address decoding to select and enable the digital to analog converter. So, looking again at my scope, you'll notice this is an offset sine wave. That's because, the voltage values only go, between positive and 5 volts. In this case, it's going from, 0 to 2.5 volts because I'm not using the entire 5-volt range. That's because on the digital to analog converter, I can set a reference voltage that gets used as the maximum value. In this case, I'm using 2.5 volts for the reference voltage. Yeah, so that's pretty much it. Actually, I could show you really quick my assembly code. It's actually a very simple assembly program, probably the simplest program I've written so far. I'm going to pull it up really quick. So here you can see these values, time 1, time 2, time 3. These are the individual time segments that I'm using in the sine wave. So in that first command, we're just looking at time 1 here. That's loading the hex value 7F into the accumulator. Then the second value is I put it out on the data bus. And then the third command there is jump to time 2. So that jumps down to the next line of the program. And then it just repeats that for each point in time and sets a different voltage value to the data bus. And so there's 20 of these commands because in each period of the sine wave, I'm setting 20 different values, and then I repeat. So you'll notice if I get down to time 20 here, down at the bottom, at time 20, it jumps back to time 1. So that's just repeating the loop in, it's just an infinite loop. It repeats over and over again because it jumps back to the beginning of the program here and starts the sine wave over again. So it might seem trivial that, you see that command jump to time 2. Well, I'm just jumping one line down, right? Why is that necessary? Well, the reason it's necessary to have that jump to time 2 command and the jump to time 3 and so on is because you want the CPU executing the same number of instructions for every point in time. So, for instance, when I'm doing this command at time 20, jump back to time 1 to go to the beginning of the loop, I want that command to take the same number of clock cycles as all the previous commands. If it wasn't like that, what it would do is it would execute more instructions jumping back to the beginning of the loop, and that would show up as a lag at the end of each sine wave cycle. So notice on my sine wave, each of those little time steps is an equal length in time. That's because the CPU is executing the same number of instructions for each point in time. That's why you have all those individual jump commands in the program, because you want each point in time to take the same number of clock cycles. Like, for example, if let's say on the program, I neglected those commands like jump 12, jump 13, jump to time 14, jump to time 15. If I neglected those commands and just let the program read from top to bottom, what you would get is, 19 out of 20 segments of the sine wave would be a relatively shorter amount of time than the last one. So you'd see a little flat spot at the end of each sine wave. And, well, that wouldn't be a sine wave. It would be a different waveform. So that's why you got to do it that way. I think I've probably belabored that point a little more than I have to, but it's just one of those things about assembly where, it looks like something is trivial or unnecessary, but there's actually a reason for it. So, yeah, this is a very, very simple assembly program, but it's kind of neat. I mean, if you can generate a sine wave this way, I mean, hypothetically, you could generate any kind of waveform, right? I mean, as long as you're satisfied with 8-bit resolution, right? I could get more resolution on this sine wave by breaking up each period into more time segments. But then the trade-off to that is it takes more clock cycles of the CPU to generate one sine wave. So the maximum frequency I could generate would go down. So there's a trade-off between the precision, the resolution of the sine wave and how high of a frequency I can go. So, because actually there's, I haven't calculated the number, but there's a whole bunch of, CPU clock cycles for each one of these individual wavelengths here. Like, actually that little red LED in the center of the screen, that is the clock signal. I mean, it's flashing so fast you can't even see it. It's probably, oh geez, I don't know. I mean, it's only about 100 hertz or so, but because I'm just running off of 555. But I mean, this sine wave is only about 0.5 hertz. It's like something like 2 seconds per cycle. So I mean, I've got estimating on the order of, probably about 200 CPU clock cycles for one sine wave cycle. So, we have an 2 orders of magnitude decrease in frequency. So there are definitely some limitations on, how high of a frequency of sine wave you can generate with this thing. But it's still pretty cool. I mean, I'm happy that I was able to do this. So I'm not sure if I'll continue to experiment with waveforms or if I'll move on to something else. This was just my latest experiment, and I thought I would share it. I hope you enjoyed. Thanks for watching.